Good morning, everyone. First of all, I would like to express my sincere gratitude to the organization committee for inviting me to share my research finding here. My name is Shujie Ge. My research primarily focuses on federated learning and data heterogeneity. Thank you for being here, and I hope my presentation will provide you some valuable insights. Today's presentation will be divided into four main sections: research background, methods, experiments, and conclusion. With the advent of big data, concerns about the leakage of sensitive information, such as personal data, behavior trends, and medical records, have been increasingly prominent. Due to interest barriers across various industries and policy-related security controls, data isolation between different professions, departments, and services has been also more and more severe, significantly impacting the performance of traditional centralized deep learning training. Federated learning has been proposed to address these issues. In federated learning, such clients retain its local data and update the locally trained neural network module to the service. The service then aggregates and averages the parameters from each client's module before distributing them back. This approach enables higher module training performance while safeguard data privacy. However, in real-world federated learning scenarios, data heterogeneity among clients can significantly degrade training performance. This issue, known as data-skewed heterogeneity, poses a major challenge to federated learning. Data-skewed heterogeneity can be categorized into four distinct types: label skew, feature skew, quality skew, and quantity skew. Label skew this occurs when distribution of label varies among principal participating clients. It is a common phenomenon in real-world applications where data collection or labeling practice are inconsistent. Feature skew. This refers scenarios where the feature distribution varies among participating clients. Such situations often arise in complex real-world environments, indicating that the feature distribution of local data may differ significantly across individual clients. Quality skew, as shown in Figure 3. The quality of analyzation or data collection may vary across different clients. Quantity skew, the amount of local data can be highly imbalanced across different clients. Figure 4 provides an example of these scenarios. But currently, most research aiming mitigating data heterogeneity remains at a broad level, with limited studies focused on specific systems. Each distinct type of data skew requires tailored methodologic designs. This paper primarily addresses the quality skew heterogeneity scenario by pursuing the FedAMKD method. Next, I will provide a detailed explanation of the operational process of FedAMKD. In the context of data heterogeneity, we are defined that the performance discarded stems from different training objectives between the service and clients. The service goal is to aggregate the local module parameters from each clients to create a global module that generalize where and encapsulate knowledge from all over data. In contrast, the clients aim to train a local module that accurately reflects their own data distribution. As the degree of data heterogeneity increases, the conflict between these two objectives becomes more pronounced, leading to the decline in the performance of federated learning. In FedAMKD, we decompose the global module and the local module into two independent modules, as illustrated in the figure. Each class trains both a local module and a global module. The purpose of the local module is to learn the client's local data knowledge and dynamically transmit this local knowledge to global knowledge module. Meanwhile, the global module aims to learn a global average knowledge and dynamically relay this global average knowledge back to the local module. Let's now dive into the method and principles behind the adaptive mutual distillation of FedAMKD. The dynamically mutual knowledge distillation coefficient is determined by each client based on the degree of local data quantity skew. In the independent homogeneous distribution scenario, each client's data quality is D over N. In a scenario with data quantity skew heterogeneity, the skew degree of the client's quantity is clarified as the offset sigma, which represent the difference between local client's data quantity and that in the independent homogeneous distribution. The hyperparameters alpha and beta are determined by applying sigma to sigmoid function. So how does the aforementioned method elevate the performance discard caused by data quantity skew? And why do we use the sigmoid function to calculate the coefficient? Next, we will provide you a detailed explanation of this process. The hyperparameter alpha, ranging from 0 to 1, regulates the extension of learning transfer from the local to the global natural network. It adjusts the learning rate by modulating the local weights between the local and global module using software labels. A higher alpha value depends the learning from the local to the global module. The hyperparameter beta, also within the 0 to 1 range, governs the learning transfer from the global to the local natural networks. Its mechanism mirrors that of the alpha, controlling the learning intensity based on similar principles. In the scenarios of data quantity skew heterogeneity, the service training objective is to learn a global module that excels across all data. After federated aggregation, the global module tends to favor the knowledge from clients with larger data quantity. Clients with smaller datasets possess limited knowledge and thus contribute less during the federated aggregation. Consequently, mutual knowledge distillation should entail the global module reducing its reliance on this local module's knowledge, as this allows clients to decrease their learning from the global module, maintaining their local module's performance. Clients with larger datasets hold more knowledge and are thus expected to contribute more to global module. In mutual knowledge distillation, the global module should glean more from these data-rich local networks. Given the global module's bias towards clients with larger data sets, their local module reap greater benefits from it. The relationship between the mutual distillation coefficient and the degree of the data skew heterogeneity can be effectively represented using a sigmoid function, as illustrated in the figure. The sigmoid function maps the input range to an unbounded output range. When the input value is less than 0, it indicates that the data quantity on the clients is below the average data quantities of all participating clients. In this case, the client should reduce its contributions to the global module, and the output value of the function will be less than 0.5. Now let's move on to the experiments section of FedAMKD. In our experiments, we utilized a central service and 10 clients. We select MINIST, Cipher 10, Cipher 100 as our data sets. We established the 3 heterogeneity levels for each data set, labeled non-ID 1, 2, 3, with the increasing degree of heterogeneity. Here, GM represents the global network's occurrence, while LM indicates the global personal network's occurrence. In our proposed FedAMKD method, the occurrence of the global module denoted as FedAMKD GM shows a noticeable improvement compared to the global module of our algorithms. We observe that FedAMKD GM's occurrence is notably higher in the case of stronger data quality skewed heterogeneity within the same data set. In summary, FedAMKD's GM global module occurrences significantly outperform other algorithms across 3 data quantity skew heterogeneity scenarios. Additionally, with the increasing data distributing heterogeneity, FedAMKD GM's occurrences demonstrate a improvement. Notably, FedAMKD LM's occurrence on the MINIST dataset is comparable to FedAMKD GM, where it is significantly exceeds FedAMKD GM on Cipher 10 and Cipher 100 datasets. In summary, FedAMKD LM's occurrence in our method outperformed FedAMKD GM across 3 datasets, especially under the condition of greater data heterogeneity and complexity. Next, let's move on to the conclusion of the paper and discuss the purpose of the future work. This paper introduced a novel federated learning framework, FedAMKD, tailored for scenario with the data quantity skew heterogeneity. In FedAMKD, we divided the traditional federated learning global and local module into 2 independent entities. Data knowledge is transferred between them via adaptive mutual distillation, mitigating performance degree due to data quantity skew heterogeneity. Future work we will explore more efficient methods for data knowledge transfer within data knowledge distillation, including the addition of intermediate intermediate technology representation distillation. Additionally, we plan to design viable adaptive mechanisms tailored to different segments within data heterogeneity scenarios. Thank you.